I made this video to explain what I've been up to for the past few months. This is an autonomous car competition where the goal is to have a car quickly plan and navigate through an arbitrary number of waypoints while avoiding all the obstacles. My team of 3 engineers won first place out of roughly 20 teams. I'm really happy about this because it was a ton of work, and even up until the day of the race we were still working out bugs in the code. Now the waypoints are marked by colored paper for us humans to see, but the car is using a floor plan map and a list of coordinates to navigate. I want to show how this type of autonomous navigation works. Keep in mind there are many different approaches, each with their own pros and cons, and now that I've been studying the subject, I think it's fun to picture some robots that I've interacted with and try to guess what kind of navigation algorithm they're using. The first thing you need is some kind of sensor so you don't crash into things. I take that back. You could actually have a robot that always does the same thing regardless of what's happening in the environment. That would basically be like a power tool. And actually a 3D printer is a good example of an autonomous robot that uses minimal sensor feedback. Anyway, the input sensor could be a camera, it could be a bumper that detects collisions, it could be like a magnetic thingy called a Hall effect sensor. It could be an acoustic sensor like a microphone. In this case, it's a lidar, so the car can actually drive in the dark. And that's a good thing because it doesn't have any headlights. This car has a camera too, but the frame rate using OpenCV and this Jetson Nano was too low, and the problem was actually simple enough that the lidar alone would suffice. I just watched an interview actually with Elon Musk where he was saying that they are turning all the cameras in the Tesla cars into photon detectors. And what he means is that cameras do a lot of image processing to translate the photons they detect into something that looks realistic to a human. And they are just simply going to skip that step and feed the data straight into the neural network. And I think this works because the neural net is just making inferences between the pixels and the labels, so it doesn't make any difference to the computer whether those pixels look realistic or not, as long as you can put accurate labels onto the images. Elon says the autopilot's response time is now around 150 milliseconds, which is really good compared to a human. I know my best reflexes when I'm concentrating really hard is around 300 to 330 milliseconds. Anyways, while not crashing into things is an important requirement, it's not sufficient for autonomous navigation. Here I'm showing a car using lidar and an algorithm called model predictive control to avoid obstacles. The behavior is not that interesting. It tends to just loop around the same area over and over again, since the algorithm doesn't consider the possibility of putting it in reverse and backing up. The robot is afraid to go down hallways or explore certain areas. A more capable robot would be one that can navigate to a desired location while avoiding obstacles. And a very simple algorithm for that would be to go into the direction of the destination unless an obstacle is detected, in which case then revert to the previous MPC algorithm. The reason this method fails is because the robot has access to only a limited amount of information, just what it can currently see with the lidar. If you want to make a good plan, what you really need is a map. And one way to do this is to preload the map into the robot's memory. This is great because the robot can make a plan before it even starts moving. The obvious limitation, though, is that the robot will only work in places where it has a map, and also if the map is incorrect, the plan could end up being very bad. And this was an actual problem that we had to deal with because the original map had the stairs in the wrong place, and so the robot always planned a path that ran directly into the stairs' real location. Once you have a map, you need to take that and convert it into a format that the planning algorithm can work on. One way is to turn the map into a graph. An easy way to think about a graph is a grid of connected points or nodes corresponding to passable and non-passable areas. In this case, all the edges or the connections between the nodes are going to be equal and bidirectional. The edge values represent the cost for the robot to move from one node to the next. You could make a more complex graph with different edge values if you wanted to account for things like hills or traffic. Now, to find a path between any 2 nodes on the map, A* is a good algorithm because it's guaranteed to give you the shortest path, and it also computes very quickly in a case like this where there are very few obstacles and the edge weights are all the same. Now that you have a path, how do you get the robot to follow it? Before the robot can follow the path, it needs to know where it is on the map relative to the path. This is called localization. The robot uses a 360-degree scanning lidar, which bounces off walls and obstacles, letting it know how far away they are. You can imagine the wall outline detected by the lidar as a puzzle piece, and the localization algorithm can move and rotate that piece until it fits somewhere on the map. As the robot moves around, it uses a Kalman filter to keep track of its location. How that works is the robot knows its starting position and where it's going to move over the next small time interval. Then the robot takes a new LiDAR scan and does the puzzle piece fitting algorithm again to find out which of those points is most likely the current pose. This is a little tricky though, because there's noise inherent in the measurement, so you have to create a model that contains the probability of any measurement given a certain true value. So here's where the puzzle analogy starts to break down, but it's as if the edges are squishy and the robot is looking for a spot in the map that requires the least amount of squishing to fit. And then it repeats this process over and over as fast as its little silicon brain can go, because the car is always moving, the LiDAR is always scanning. So the path is a list of points that the robot must pass through to reach a destination. The first thing is to determine which point you're going to aim for, then figure out how to get there. One way to determine the target pose or point is simply to delete all those poses which are behind the car, or the car has already visited. Then the target can be the next one on the list. But an even better thing to do is to look ahead some number of steps and target that one instead for a smoother trajectory. Once you have the target pose and the current pose, then you can calculate the difference between them and calculate a heading to close that gap. The program also calculates a heading to correct for rotation error, and then it returns a weighted average of the two. The steering command is generated by a PID controller using the standard 3 constants and 3 error terms. These weights and PID constants are important tuning parameters for smooth navigation. One funny thing that can happen when you use the difference in angle for rotation error is that the angle is close to 2 pi, it can wrap around back to 0. So instead of saying I need to go to 6.28 radians and I'm now at 6.29, so I should go back a little, the robot will say, oh, now I'm at 0.01 radians and I need to go up a lot to get to where I'm headed. That makes the robot spin in a circle for no apparent reason. So what you can do to avoid this is to take a vector pointed directly to the left of the car and use a dot product of that with the desired heading as your rotational error. So if it's a left vector and you have a positive dot product, that means you need to turn left. And if it's a negative dot product, that means you need to turn right. And 0 means the destination is directly in front of you. So what made the difference between winning and losing in this race? Well, I hope you can see there were tons of challenges to overcome just to finish the course, and the time constraints made it very difficult to implement and tune all the algorithms. As I said, we were still tweaking the code right up until the deadline. So prioritizing and solving problems was big. It was a team effort, so writing code that was clean and readable is very important. And for the purpose of tuning parameters, writing the code in a way that was easy to test and iterate saved so much time. My favorite part was realizing that since everything was running on a microcomputer, the code had to be very efficient. There's plenty of times when the car would just slow to a crawl or slam into a wall because the code didn't execute fast enough. So planning an efficient path, solid localization and control models, and tuning to avoid collisions all came together for an excellent race. And I want to say congratulations to my teammates Derek and David for a great result, and it was a really fun project, and I'm really happy that we did it.